So some of you have seen a little bit about this work. I think it's a good work. And Pavan is in a hurry to leave, so he prepared a rather short presentation, I would say. Much more work than what I've seen in these slides. So hopefully you will get a good picture from this.
Hi, Pavan. My topic is distributed source coding algorithm framework. My source is my Coset code correlation. So I've been working on this topic for the past 2 years. My first year I was with the Rutgers. So I thank Kaivaram for my entire master's thesis. So I'll get started. So the outline of the talk, I'll start with a brief introduction of what distributed source coding is. Then I'll dwell into the prior work. Then I'll give you the contribution of my thesis, what my basic contribution in the thesis is. I formulate the distributed source coding problem, and then I'll give you what are Coset codes. I talked about Coset code correlation. I'll talk about Coset codes, and then I visualize different algorithms using Hypergraph, with which I represent the joint probability distribution function. And I make a lot of assumptions because as such the problem is tough to solve, and I clarify them together with the formulation. And then I'll give you the distributed source coding theory and then the algorithms I propose in this for Coset code correlation. And then I'll show you the results. So, what is distributed source coding? Distributed source coding is basically we have multiple sources, and typically like sensors, and they have lots of information which is like correlated. Correlated information obviously means that the joint entropy of the sources is less than sum of entropies of individual sources. And these sources are transmitting information to a central receiver. That means that the decoding is joint, even though each of them is individually sending information. So, if sources could do cooperation, then they can achieve the joint entropy bound. That is the typical source coding problem. But if there is no cooperation, can they still achieve the joint entropy bound? And that topic concerns with distributed source coding. So why do we need distributed source coding algorithms? Obviously for achieving joint compression bound, basically achieving the joint entropy bound. And for example, in sensor networks, you have sensors which are power and bandwidth constrained. So the rate reduction helps increase the life of sensors by reducing the power and bandwidth used as well. So distributed source coding algorithms have many uses in sensor networks. So I'll briefly introduce you to the prior work in distributed source coding. So that starts with Slepian-Wolf, work by Slepian and Wolf in 1973. And then this Slepian-Wolf work is for 2 sources instead of multiple sources. The extended Slepian-Wolf region, I don't know who first talked about this, but it's a simple extension to the multiple sources, and that's for multiple sources. And then the first practical algorithm for distributed source coding is discussed, which stands for distributed source coding using syndromes. This was proposed in 2000 by Pavan. And then I'll give you a brief overview of how channel codes can be used as source coding, which is a very important for this. So the Slepian-Wolf region is basically this region. It's for 2 sources. It's basically a rate pair, set of rate pairs which are achievable. So this is Slepian-Wolf consider the problem of 2 sources transmitting information to a central receiver, and they considered it as communication with side information. That is, one of the sources transmits itself completely, so it's known as the joint receiver. But the other source is not known, and you have to basically compress it and send it based on side information at the receiver. So they proved that you can achieve this region, which is basically saying if you have if you send x1 at complete entropy, then you can send x2 at the conditional entropy given x1, which is equivalent to the joint compression bound. So if you have a central receiver which can do joint decoding, then you can achieve this effectively the joint entropy bound. So this is another point where you send x2 completely and you send x1 as side information, and this is the convex hull of all regions. Extended Slepian-Wolf region is basically an extension of this to multiple sources, and the way you get this basically this: choose any n-1 sources. You can do that in n ways, okay, and then assume that is already known as the receiver, and you send the leftover source using Slepian-Wolf coding with the rate of h of x and here. This can be anything, and this will be the common system. Okay. So in this case, I have considered 1 to n-1 sources. You can have n permutations. So you send this, and then now you assume that these sources are sent losslessly, and consider that problem for n-1 sources, and that will give bound on n-1 sources, and so on. So all this, if you consider all the regions which are formed by this, you will have n dimension. Obviously, this is a region in n dimensions because you have n sources and you have n tuples, and all such rate points form an corner points of an n-dimensional plane. So, and the plane is given by this equation. I'll just give an example for 3 sources. So if you look at 3 sources, this is R1 star. Star indicates that basically the figure is drawn with the shifted origin. Okay. So it's basically tough to show it. I'm not that good at it. So basically this is R1 star, which is slightly shifted, so that this plane aligns with the R1, R3 plane. So it's shifted so that this plane, and this plane are aligned on R1, R2 plane, R1, R3 plane, and R2, R3 plane. Okay. So if you look at this region, basically this part over here, this is R1 plus R2 plus R3 is joint entropy of this, and the corner points, 6 of them, are obtained from the previous through this procedure. So if you look at this, you have 2 corner points here, and you have 6 corner points here, and in a general n case, you have n factorial corner points in a n dimensional plane, n dimensional.
How many faces are there? Like
Here?
Yeah, how many
I
faces?
think 2 to n, I'm not sure. 2 to the n minus 1 must be.
4, 5, 6, 7.
Yes, 2 to the n minus 1.
minus 1.
Yeah. Okay, so that's the theoretical work which is done for distributed source coding. Now coming to the first practical example which was given in 2000, basically consider this small example which illustrates how distributed source coding is done. Consider 2 sources x1 and x2 which have the same alphabet, which is the binary representation of the alphabet you can write. So which have the same alphabet, and they have a correlation which is the correlation between x1 and x2 is such that the distance between x1 and x2, the Hamming distance, is at most 1. Okay, so the Hamming distance is at most 1, and now x1 is completely transmitted. So x1 is known as the side information at the receiver, and we can see that the total entropy in x1 and x2 is h of x1 plus h of x2 given x1, which is.
Wait, you lost me with the correlation and Hamming distance. What do you mean? The minimum distance is
for example,
the minimum distance is 1, right?
No. Okay. For example, x1 is 0, 1, 1. X2 can only be one of the 4 this ones, which is 0, 1, 1, 0, 1, 0.
Right, so you're constraining the 2 sources. Okay.
Yeah.
That he calls correlation, in the sense that they're related.
Right. They are not independent.
Understood. You picked one, so you dictated what the others cannot be.
So they have in all 5 bits of information in them, joint information. But if you encode them separately, you send 6 bits, and can we achieve better than that? So the way to encode is basically bin x2. Basically, x2 is divided into bins. In this case, 4 bins, as 00011 and so on. Okay. And so if you look at this form is linear code, and these are the cosets of the linear code,
which are 3 apart.
which are having distance 3 apart. So now the way to encode this is transfer the bin index with 2 bits instead of sending x to itself. So instead of sending x to, if you send the bin index, you will be sending with 2 bits. And can we decode it losslessly? You can see that decoding is lossless, because given an x1, only one of them can occur in a bit. So immediately after formulating this, the problem of 2 binary sources x1 and x2 correlated by this. Basically, x1 and x2 are 2 binary sources, and x2 is kind of output of a channel. So if they are correlated in such a way, the total entropy is 1 plus h of n, where h of n is entropy in the noise, and h of x2 given xn is h of n. So looking at this problem, it's still a Slepian-Wolf this one, but then we are looking at practical. So you know x1 completely, x2 is kind of side information. So to solve this problem, what we do is we consider a very good channel code for this channel. Okay, that means achieving capacity. Let's assume that you can achieve capacity on the channel using good linear code, and this good linear channel code achieves capacity. So since decoding is lossless, you can achieve a rate of 1 minus h of n over the channel. So what does that mean? That means that if h of n is the entropy of this, you can send 1 minus h of n bits from here to here. So that means that the linear code achieving the capacity will, if you look at the coset partitions of this one, each of them will have a noise sequence. If you look at the so basically every typical noise sequence lies in a different coset. That is why you are able to achieve capacity. That is because if you consider a linear code, then and you transmit a linear code, but once you receive a received vector, the way to decode it is find the coset in which it forms and remove the maximum likelihood noise sequence of the corresponding coset. So if you are able to achieve capacity, if you add these maximum likelihood noise sequences, the probability should be equal to 1. So noise basically forms a coset code of the linear code. So now we know that given the noise we can achieve capacity on that. Now we will give a distributed source coding algorithm for x1 and x2. So now x2 coset partition x2 over G, use the same linear code. We know that x2 can take all possible values because it's Bernoulli half. So you coset partition x2 over G, and then send the coset index of x2. Okay. So now decoding is lossless because given x1 as side information, okay, x1 plus n, now n forms a coset code of the linear.
Show me the system diagram again, go back to this.
Right.
Right, so we now go forward one slide, we're assuming we know, go ahead. Right, given x1, right.
Okay. Now n forms a coset code. That means all typical sequences of n lie in different cosets. Fixing an x1, you'll have x1 plus n also forming a coset code, right? So that means all possible sequences of x1 for different instances of n lie in different cosets. So given a coset index, you know which x2 is transmitted. x1 plus n is nothing but x2. So given a coset index, you know which one of them is transmitted. And so decoding is lossless. So now the distributed source coding problem formulation for multiple sources. Now we have n sources here which are specified by the joint PDF.
Oh, excuse me, I don't know enough about this area. This is new, old, you're exploring it. What's the...
Okay, we have, they have algorithms for 2 sources, but there's no extensions for multiple sources.
Right, so there's no...
When you say they,
Ramchandran and George Yates, all this, and George Yates actually worked on LDPC codes that
what
were
are you using?
George Yates.
Georgiana.
Yeah. That's it.
There are references on multiple sources, but you haven't included them in the paper.
Yeah, they have considered 3 sources also. I don't exactly remember the reference. 3 sources was considered, but still it always boils down to the Slepian-Wolf side information problem.
Did he spell Georgianis right in his thesis?
Yes.
You're the expert on that, right?
He did.
Yeah, but you're the expert on whether it's spelled correctly.
Okay. Now coming back to the distributed source coding problem formulation, we have multiple sources which have a joint PDF, which have highly correlated information. You take n instances of each of these random variables, and then send them through a distributed source coding block. Basically, this is a f1 is only a function of x1. It doesn't depend on these. That means that's why it's distributed. If this was joint, then you would have had only one f, which would have taken all of them and then compressed into single information bit to the central receiver. Now f1 encodes x1n into y1 and so on, and these are sent instead of x1. So the problem basically is to reduce the sum rate of all of this, so that we can achieve a good compression.
So you're not telling us yet what x2 is.
F1, F2 are each of them are encoders for source 1, source 2,
And they don't talk to each other.
they don't talk to each other.
Right. But like so the case of the 2-terminal thing you're going to do Slepian-Wolf, like for
Yeah. So for 2 source things, in literature what has been done is basically this is sent completely without encoding, and this is sent as side information. So that's what has been done. But I consider compression using 2 different.
So you sometimes seem to use side information, like in the case of 2, right?
Right.
You like here you said, oh, sometimes you send x1 and then you send x2 with side information. Is the x2 given x1 sigma the side information, or is the x1 the side information, or is it just the
it's
side
x2 given
information?
x1. X2 given x. I mean.
There, I think earlier
No.
in your presentation you referred to x1 as the side information.
Yeah, I made a mistake. They don't send x2 as side information. x1 is known as side information. They send x2.
So does anyone have 2 knows x1?
Huh?
Or not? Does anyone have 2 knows x1?
No.
That means that f1 is equal to
No,
1.
that is the Slepian-Wolf result. The Slepian-Wolf result says that. Oh, okay. It basically says that if you don't know x1 and x2,
right,
even then you can compress at the joint compression, joint entropy bomb.
Okay. And in the hand waving way, how is it done?
It's basically again random codes. So you take information theoretically. I don't know whether I'll do it right, but I think.
The argument is sort of that example you did, right?
Yeah.
Right.
So I'll.
Richard we just came in.
No, he was here.
Oh, he was here.
Yeah.
Okay, I'll go ahead. So if you look at this, there are 2 sources, x1 and x2. They have this alphabet, and they are correlated. Okay, and they are correlated in a way where they are separated by at most 1 bit. Okay, so if the way to do it is, so x1 is completely known at the receiver. Okay, now we are trying to transmit x2. Okay, so what we do is we bin x2 like this, so that the distance between 2 of them in a bin is 3. Okay, now instead of sending x2, just send the bin index.
Which is 1 out of 4, so you have to send 2 bits. Right. Once you get one of those bins, then you know x1, then you know which of these two is closest.
So for example, if it's 0, 0, if x1 is 0, 0, 1.
So I guess the correlation is already exploited when you design the.
You have to know the correlation.
Yeah, you know the correlation. Yeah, that's right. You know the correlation structure, but you don't know the actual value of x. Okay, so distributed source coding problem is designing of these encoders so that you can get a maximum compression. It's a general formulation of the distributed source coding problem. So looking at it without the graph, you have n sources x1 and x2 with random variables x1 and x2, the alphabet xi, and there is a joint distribution which specifies the correlation given by x underscore here. And you take n independent instances of random variable xi, which is xi to the n, and you use fy to get yi. So this is the design parameter. This is what we had designed for distributed source coding. And basically, this encoding fy implements the distributed compression algorithm. And we have a joint decoder, and that is what we make it with.
Turning the picture again, back up one. Right, so you're blocking the axis, you're applying some function to them.
Right.
And then those are what are transmitted to the central receiver along independent rails. And you need to figure out what the original axis was.
So the contributions from this thesis are basically we use hypergraphs to represent joint PDF, and we formulate the distributed source coding problem on hypergraphs. Then we consider a specific correlation structure on hypergraphs and group theory on hypergraphs. We specify algebra on hypergraph, and then we give an algorithm, distributed source coding algorithm for Coset code correlation structure, which can also be viewed using hypergraph, but it's more it's useful in the sense that the algorithm for encoding is polynomial time, so it's very fast encoding.
So what you are transmitting on the channel itself is a single symbol, or it's like y1 to the k, there are k channel symbols?
You can consider still that as a single symbol on a higher output.
Okay.
The thing is, I cannot represent it using y1 to the k because the compression here can be more and the compression here can be less. I can choose to, let's say there are n symbols, right? So I have n instances of each of them. So I have n into n binary digits to be transmitted here.
But the symbols for each of them, x1, x2, all the alphabets they are different, right? You said they are xi1, xi2 up to.
Yeah, and I'm just saying, for example, consider a binary source. Okay.
So but it takes n of each alphabet,
Right.
and then it output is just one symbol.
I'm saying it one symbol, that doesn't mean that it has the same size as x1. It can have a different size.
So if you plotted this in binary, he could have put an n here and k there, and then
So
k1, k2.
the overall compression is what matters. How much I spent on each of them is not a criteria. Okay.
Actually, a question I have is the following. So do the individual sources, do they need to exchange the data between themselves?
No.
Not at all.
No.
The same as the Slepian-Wolf. They just stream whatever, there is no any cross talk between these entities.
Yes.
But I guess they do need to know the correlation.
Yeah, they do know.
The correlation.
Basically, it's more like I know the joint correlation structure,
Yeah.
and then I give a matrix to each of them, and I multiply by them. That's it. Like, so they don't need to know any of this, but they are in fact, they know the correlation structure. That's why they know the matrix. So I said that I formulated distributed source coding using hypergraphs. So
I'm going to back up. So actually, I've always had a question about this particular thing. Back to the picture again. Okay, so the basic premise is that you want to have something that's done in a distributed manner, so that source 1 can formulate F1, and source 2 can formulate F2, and so on.
It doesn't formulate. I give the F1 to it. It's, source 1, if it knows the complete correlation structure, it can figure out what F1 is. But the idea is these are more like sensors which are very dumb. So what I do is after setting, there is an initial phase where I give the F1 to X1, F2 to X1.
Now I understand. You answered my question. My question was dumber. Was the main issue is that while this thing is actually working, if you didn't have these Fs,
Right.
if you had some arbitrary code books, you wouldn't achieve optimality here. They don't have to even talk to each other before they transmit.
Okay. Now, looking at the hypergraph formulation for distributed source coding, we will first define what a hypergraph is. Hypergraph is basically an extension of a general graph, but a general graph will have an edge passing through two vertices. Edge passing through multiple vertices. So basically, a hypergraph is a graph in which you have vertices and edges, each edge passing through multiple vertices.
Can you make a picture of it?
Yes.
Yeah, there'll be a lot of pictures.
So,
Just go on this slide, don't go further.
PDF of, so if you have multiple discrete sources, we can represent the PDF using the edges of a hypergraph. So for each joint event, we represent it using an edge, and we can represent the PDF on a hypergraph. And obviously, because each discrete source cannot.
Before you continue, can you just bring the pictures?
Yes, so let's say that there are three sources, and they have a discrete alphabet. Okay, x1, x2, x3 are the three sources. Then you can represent a joint event as a hyper edge. This edge passes through three vertices instead of the general two vertices which you are used to doing.
No, that's not clear yet. Go ahead.
Okay. So if you represent, for example, so this is a joint event. That's what. So the joint event is this and this has a non-zero property. So if you have x1 is equal to 1, x2 is equal to 1, x3 is equal to 1 is a joint event, and the probability of that is non-zero. If the probability of that is non-zero, then we represent it using a hypergraph.
Isn't it just coloring problem of a normal graph? That whatever you call your multi-vertex edge is actually a combination of several joint edges. You just used to have the same color. Because to me it looks like still as a normal graph.
Yeah, you don't see, there is no edge defined between this and this.
Yeah, that's why I said it was a confusing thing.
It's confusing because it looks like a normal graph, which now it's few edges were colored so they represent a certain entity.
I think what he means, though, another way possibly to draw it, you correct me if I'm wrong, you take those three upper vertices, draw a circle around them and call that a super vertex or something.
Super vertex, yeah.
And
then zoom in.
I draw an edge from that super vertex to another super vertex.
That could be an edge, not a vertex.
So
normally one edge joins two vertices. Here
Right.
one edge can join more than two vertices.
Well, when you take the vertices and put them into a circle and then I draw an edge there, I'm thinking graphically that represents that it's connected to all those vertices. That's what I think I'm seeing here.
So in your case, you always have an n-part-type graph, right?
Yeah, I always have it.
And the thing that corresponds to an edge in a normal graph is an n something.
Yeah.
One from x1, one from x2, one from x3.
Yes.
And there's no overlap between these super vertices, right?
What do you mean by
These vertices, you can't have an edge.
I have membership in this group and have a vertex that's a member in this group and a member in
It can be.
this
For
It can
sure,
be.
they almost
See,
all
for example, these two are there in this edge. These two are there in this edge also.
The way he draws it, usually like he says, these are same, these are same, these are same. Right? These could be same, right? Same alphabet members.
Yeah, numbers, I mean, it's just numbers, but different vertices. As well.
So this is just an event, and there's no event between this guy, and this guy. This guy, and this guy. There's no event. Just describes what happens. The only condition here is that he doesn't have weights, so they're all equally likely. And that's what he describes. Now you could put weights, and then if you put weights, then there would be all these events. They would have.
So basically, by this hypergraph, you're defining basically a joint alphabet.
Yeah.
Or
Yeah.
Joint PDF.
an alphabet because he's enumerating all possible combinations.
Yeah, each edge represents a joint event.
Joint event. And all events have same weights because he didn't assign weights to edges.
Her terminology is not too bad, actually. Since really all the possibilities is non-zero probability.
Yeah. So basically, only all edges
events,
for it's the support set, right? For the support set is basically all events with non-zero probability. So set of
I think if you draw for two like x1, x2, a bipartite graph for x1, x2, and then you say that if I want to add another event, then the graph resulting will be like this.
Yeah.
It will be okay.
So I come the other way around and say that that's the projection on this. Anyway. So the graph is n-partite, or like in this case it's 3-partite, because there is no edge going here. There is no edge passing between two vertices of the same vertex set. And so the degree is also same in this. For example, the degree is number of edges passing through a particular vertex. In each vertex set, we observe that in this graph, they are the same.
So wait, go back to the last item there. Every vertex in a vertex. So what is a vertex set the same as one of those?
Yeah, this thing is a vertex set, and there are 3 vertex sets. And
so wait, in your case, so the picture doesn't correspond to the bullet.
It does.
It does. Every vertex in a vertex set has the same degree. So this is a vertex set. Degree is 2 here. Here degree is 4, and here degree is 4.
Ah, okay. All right, I understand.
Which is not a general sort of form, but that's what he's considering.
Yeah.
And he's taking that as an example.
As an assumption for him.
So a projection on this is basically a projection on subset of vertex sets is defined as the hypergraph of joint PDF of the subset of sources. Okay. So if you look at these 2 vertex sets, the projection of it's basically like an n-tuple, and it's projected onto an n-1 tuple. Okay. So if there are 2 edges corresponding to this, that maps only to 1 edge. It's basically if you have a joint event, the property masses get added. So it's called a regular projection if the number of edges which map onto each edge here is constant. For example, here it's a regular projection because number of edges for any edge is 2 which map onto it.
So that's referring to edges in the normal graph sense?
Yeah, you can still call it a hyperedge of order 2.
No. So if the number of edges, so if you read that regular projection, if number of edges, number of hypergraph edges, mapped onto each
Edge in the projection. That's what
each edge in this projection. So for example, corresponding to this, and this are the 2 edges in the graph.
Okay.
So it's basically the probability mass projection itself. So it's called a regular projection if the number of edges corresponding to the mother graph in this graph is constant. Then, so this is the main assumption we'll make. We call it the regularity assumption. That any projection on this, on any subset of vertices is regular. Okay. So, for example, we can see that the degree is 2. So projection on trivial projections are regular because if you take only one vertex set, the degree is 2, number of edges corresponding to that is 2, and so on. If you take any subset of 2 sources, all of them are regular. If you take these 2, this is regular.
So when you do a projection onto a subset of vertices, you really mean onto some kind of collections of vertex
Yeah.
sets.
Subset of
You're not allowed to just pick any random collection
Yeah.
of those. Right?
So, does it mean that the joint PDF was symmetric? It hasn't shown.
Joint PDF?
Was symmetric? Because when you're taking a projection, you're adding up all the events, probability of all the events.
Okay.
Yeah, I think that's what it means.
This is just marginalization.
Yeah,
Marking
so
yes.
What does PDF symmetric?
That's what he does.
No, the original joint PDF was symmetric. That's why you're saying that.
Symmetric with respect to what?
Yeah, okay, I call it regular.
It makes this property happen.
Oh, you mean that on
Any projection is regular.
So go back to your three graphs, just so that I.
He's using the word regular to mean what you
Right,
call
so the very first thing you did was
Yeah,
you
and
it's
took
what
out
its
events.
definition
Those
is.
events are denoted by your solid and dotted lines. Then what you're doing next slide.
Next time defining
Next slide.
different properties.
Right, now next,
So that's
so that's the first one, that's the first collection. Now the property there is,
if the number of edges which map onto the next symbol is constant, then it's a regular projection.
okay, so we have 1, 1, 1 to 2
Yeah.
for each, okay, next.
So yeah, basically my main assumption for this is that any projection on this is regular.
And again, on a regular
Okay, back
meaning,
up.
The projection on
Okay.
and regular meaning exactly what? Because I heard a few words like regular is the same as symmetric, or what exactly did you mean?
regular is this.
No, sorry.
Any projection on the PDF hypergraph is regular.
Yeah, well, what word regular means?
Regular is a regular projection.
Some changes come.
These edges of projection.
I have a question. Did you select such a, did you take those assumptions just for the ease of presentation?
No, as such DSC is a tough problem to solve. So if you look at, okay, I'll tell you the motivation why I choose regularity assumption a little later.
So
But
you
it's
chose
for proof of
regularity.
theorem. You need that.
But you chose regularity. You can't take an arbitrary graph and decompose it that way. Now look at this. This is a decomposition essentially. This graph that you've drawn up there is actually a combination of these three graphs that you.
Yeah, but given any three of them, I don't think we can reconstruct.
Sorry, what?
In a general case, we cannot reconstruct the original graph. It's like giving joint distribution on any n-1 subset of sources.
Gotcha. And you start from there and decompose it into a bunch of regular
Yeah.
graphs always.
Yeah.
For what assumptions on that graph? None?
On these graphs? No.
On the top graph. Okay, so it can be an arbitrary graph?
This thing?
Yeah.
This also is a regular graph. A projection on itself also should be regular.
Yeah, I'm just, then I guess I'm just lost, so I need help. I guess I'm just
Yeah,
lost.
you can say that there is no assumption on that. Because the regularity on individual sources, right, makes it basically make sure that if you take projection on to a single vertex,
Regularity on I'm getting hung up on Leo's term again. So the regularity on the graph stems from the fact that you're taking these three at a time in part-time manner.
So his example's regular? Oh, I guess you're just asking him.
I'm really asking.
He's only going to consider graphs with this special property. After he looked at this example, he carefully drew one that met this condition, right? But it doesn't derive from anything. He's not going to worry about that. He's simply going to assume that his hypergraphs have this property.
So he'll give a motivation for why he does this.
I think in order to keep us moving, do you have also, this is a graphical representation of the
Right.
problem. Do you have a sort of, algebraic or group theoretical representation where you actually don't need any pictures and you just write expressions or whatever? Is it possible?
I mean, I don't have the slide, but
Is there an alternative language to express?
Yes. Okay, so this is another projection on other set of vertices. Now I'll tell you what compression of this hypergraph is. A compression of PDF hypergraph is similar to the maps which I have defined in the problem, and you have Fi, a map from each vertex set onto a vertex set in the compressed graph. But I didn't show compression still. So if you look at this, there is a map from these two vertices onto a single vertex, and these two vertices onto a single vertex. So this is a compression on a graph, right? In this case, even after compression, you didn't lose any edge, right? So all the edges here are visible here also. And basically compression, while compressing, if there is an edge, for example, if there is an edge here and an edge here, those two edges will go onto a single edge, then there is a loss.
You can explain your projection as marginalization in a trivial way, right?
Yeah.
So that's an answer to Leo's question. You don't have to give him any deep answers. Right?
Yeah, sort of.
Projection is marginalization.
Yeah, it is.
So if you marginalize and you get sort of like a structure that's what that you.
No, but my question was actually not that. So that's I realized. So my question is that since this graphical representation caused so many questions, is there any alternative like algebraic language where you actually can address the whole thing? Like group theory, you don't really need any pictures at all.
We can.
I think we should do that.
He's going to talk about group theory.
Okay. So lossless compression is compression where there is no loss of edges, and you can see that a maximal compressible hypergraph is a basically if you can compress this graph using the maps f1, f2 and so on and f3 in this case, so that you get a complete hypergraph without loss, then it's called a maximal compression. For example, in this graph, if I do this kind of a compression, you can see that there are 8 edges here. You have all 8 edges here also. Okay. So this is a maximal or bound achieving compression. You can't compress beyond this.
So what does bullet number 4 say?
Okay. So in this case, suppose instead of compressing these two, I compress this and
something is wrong with the consent.
1 and 4. 1 and 4 will screw you.
1 and 4.
yeah, 1 and 4. If I compress 1 and 4, there will be a loss. In the sense that, for example, if I take this edge and probably not.
Yeah, there is green edge, green solid and
Yeah, but it still goes to different places.
Okay, 1 and 4.
1 and 3.
I guess I can compress all of them and make one.
Having 1 and 2. How many different combinations?
Okay, we'll choose a compression here, then maybe that will help. So if I this and
I think if you do one compression on the left, and then I think it'll be illustrated. Just do one.
okay, if I do these two, if I compress these two, okay, I have this edge and this edge, right?
Right.
So both of them will map onto the same edge. So that means I lose an edge. Then there's a loss in cost.
So what is, like I keep reading the English of bullet 4.
It's not
Compression is a PDF hypergraph with onto maps.
The bullet 4 was supposed to be deleted, right?
Compression.
something strange in the formation of the sentence.
I think we can ignore the bullet 4.
Okay. So the maximal compressible hypergraph is one where you can compress it to the complete n-parted hypergraph without loss.
So go back to a second. Compressible. Okay, so what is the compression?
The compression is set of maps F5. Set of maps F5 on each individual vertex set. Those are onto.
Yeah, I understood that block diagram of compression. right? And I sort of understood that it, you know, for 2 that it's Slepian-Wolf, right? And now the question is, what is it in relation to these graphs? It seems
Okay,
like
this looks like this is an alphabet of x1, right?
Yeah.
x1 to the n.
Right.
You take n instances and the alphabet looks like this.
Yeah.
And then you have a map fi, which maps onto yi, right? So these are the yi side. And the compression is so that you want to compress the information. That's why you have to encode 2 of them as the same thing.
Yeah.
So you're able to. So it's kind of this specifies a map between x1 to the n and y, and this is a map for x2 to the n.
Okay. And somehow there's no loss in that map?
Yeah.
And is that...
I mean, I chose so that...
If you're constructing a tricky example, like where you work for a while to figure out that you can either send, so you're still communicating a 3-tuple, right?
Yeah.
And you're saying, oh, any 3-tuple in the bottom graph, right, has a one-to-one correspondence with a 3-tuple in the top graph?
Yeah.
And that's not that's because
I mean, that's not just because it's regular.
But you somehow spent a fair amount of time to build this.
Actually, I don't have to spend a fair amount of time building this because I can construct it from Coset coordinates.
Right.
So now I'll give a brief introduction to groups and specify the group structure on that.
I'm sorry, I'm just having too much fun with this. Go back one.
So you had one more little thing where your dots merged, but somehow we missed that little bit of excitement.
The goal is to get this complete hypergraph. If you can do that, then you can achieve the bound.
Now, could I ruin things for you by, let's see, drawing an edge through 1, through 4, 2, and 4?
1?
No, 4, 2, 2, and 4.
Okay.
Okay, so now I've got 9 edges.
Right.
Right? And there's no way you could represent 9 edges.
But it probably doesn't meet his regularity.
Regularity conditions are not such.
No, I'm not saying that whenever it satisfies regular, I can do
I'm
this.
I'm just playing with the concepts. You just told me it's not regular, so it would not be regular because the bottom one down there would have 3 edges coming out of it.
I can still compress using these 2. I can compress just those 2.
Right. I must walk. I must crawl before I can walk. All right. The regularity is coming a little bit more into focus for me. All right, go ahead.
Now, a little bit of literature search on groups and cosets. So, set S with operator plus is called a group if the set S is closed, associative property is satisfied, and existence of identity and inverse. All these properties are satisfied, then it forms a group. In addition to that, if it satisfies the commutative property, it's called an abelian group. So a subgroup is basically a closed subset of a group. The statement is in fact 2 theorems, in fact 2 statements. One is take a subset and it has to be a group under the plus. Then it's called a subgroup. That's the actual definition. But if it is just closed, other properties follow, and so it forms a subgroup. So a coset partitioning with a subgroup A over S is defined like this. Like, first of all, I'll give you a small theorem and then give the partition algorithm. If you choose element C and V of S, okay, and form 2 sets C plus A and B plus A. This means that form all possible elements, all possible combinations of C and elements in A, add them and form a set. And similarly for V, do the same thing.
A question here. Are you considering Abelian case or general case?
Abelian.
Only Abelian, so it's...
I mean, yeah, my
you
case...
don't distinguish between left coset and right
I don't.
coset, there's the same.
Yeah. So, if you do this, then the property is that the size of set C and size of set V is the same as size of the subset, And also either C is exactly equal to B or the intersection is empty. So this is the property satisfied by groups and subgroups. So coset partitioning is achieved using a simple algorithm using this property, and that is you start off with C0 set A at I is equal to 1 and choose some C which is not in the union of any of the previously formed cosets, okay, and form CA is equal to C plus A. So this will be entirely different set from all of them from this property, and you can partition your space into cosets. So now the group property is also followed in linear codes over finite fields, because linear code is also a subgroup, and we can specify similar group and subgroup structure over the linear codes. So a linear code is basically an n cross k binary matrix, or for example any matrix with f to the n, where f is instead of 0 1 I can have a finite field.
So what plays the role of plus in this particular case?
Vector plus. Vector A plus vector B.
Modulo 2 or
I'm
G
in
whatever. So I want him to answer.
Okay,
What is
field
the
is
definition of the group operation in that particular binary case?
the field is F2, right? So you form a vector space over that, F2 to the n. Okay, the set of vectors over F2 to the n form a group.
So what's the name of that operation?
Extension, group extension.
No. When you have two elements of the group, you add them up. It's just XOR.
Yeah, or binary. Yeah.
For binary. Yeah.
So once you do the coset partitioning of this elements in F to the n in general, so you do the coset partitioning using the subspace spanned by G. Yeah.
Sorry, this is the previous slide for 1 second.
You
Each subgroup A, you take any element from A complement.
Okay.
Right, and then so add that to every element in A. So you get one set. That is one coset of A, is it? That's all.
No. Okay. So S is the mother set.
Right. Yeah.
Okay. A is the subset of that. It also forms a subgroup. So if you take any element,
Not in A.
need not be not in A. It can be any element. If it's in A, you will get A. Okay. So if it's not in A, you will get another set. Okay.
So that's called a coset of A.
That's called a coset. Basically, the whole process is called coset partitioning of S with A.
Are you like?
Okay.
Is your third line correct?
Huh?
Is your third line correct? Yes.
A has to be different. Notation mismatch.
So this A is not the same A as in the beginning.
So what are the sets C1 to Ci minus?
Those are the cosets.
But how are they defined?
Okay, first it's an algorithm which defines them. Okay.
Right.
So you initially start with C0 and set it to the subspace A.
How do I choose C1?
You choose any C which is not in
Oh,
C0.
yeah.
Okay.
I got it. Not in the last one.
We're never gonna finish if we're gonna discuss this word.
Similarly, we can define cosets and over a linear code. And the beauty about linear codes is that we have a parity check matrix H which indexes the coset directly using syndromes. So if you take G and the left null space of G, that indexes the cosets spanned by the linear code formed by G. So now comes the definition, and my algorithm is on coset code. So a coset code is a subset S of the full vector space 0 1 to the n, okay, f2 to the n of size 2 to the n minus k. Okay, so it has size 2 to the n minus k is a subset of this, and it's called a coset code if every element of the set lies in a different coset of G. Okay, it's more it's like saying S forms a coset leader set. Okay. So now comes the main assumption. The first assumption is that any subset of sources is uniformly distributed over its support set.
Isn't it the same as your regularity?
Yes, that's the same. That means that hypergraph is regular.
Yeah.
That's the first assumption. And assumption 2 is that assumption 1 is satisfied. So, and every subset of sources has integral entropy. Okay, what I mean by this is basically the number of elements in the hypergraph is 2 to the hi or some I in every vertex set. Actually, this thing is not necessary. I will give an example. Okay, so for example, here you have 4 vertices in each, 4 in this, 2 in this, and 4 in this. Each of them, each of the vertex set has an integral entropy, right? And the number of edges in this is 8. So even that is integral entropy.
So this integral entropy, right, for each source is measured with respect to some log base, right?
Yeah.
It has to be a common log base
It's
for all
2.
of them?
It's 2 for my case. Because I use linear codes only on field 2.
Okay. Somehow usually the everything is completely generalizable in the
Yes,
graph,
yeah.
right? So if it weren't 2, what would the condition be? So you're requiring them all to have integral entropy subject to log base 2.
Okay, the group theoretic formulation of hypergraph in fact shows that it can be anything. It doesn't have to be log based integral entropy for that. Okay. But the problem with that is if you don't have a finite field as the index of that, I don't know whether you have an algorithm for indexing the cosets and polynomial. Okay. So assumption 2 is again every subset of sources forms integral has an integral entropy. In fact, if assumption 1 is satisfied and the number of vertices have integral entropy and the total number of edges have integral entropy, this every subset will have integral entropy based on the regularity assumption. So now I'll try to motivate why I consider regular this one. So assumption 1 basically says that if you consider a set of typical sequences, jointly typical sequences over all n sources. Okay, we know that every typical sequence is approximately same probability, right? And on every subset of sources, they also are typical. Jointly typical means on any subset of sources they are typical, right? So on any subset of sources, they will have equiprobable events as n tends to infinity. So that means that every subset of sources is equiprobable, and so my assumption is valid asymptotically for any source joint PDF. So assumption 2 is kind of a simple extension of this, but for the first part, it has an integral entropy. You can always choose, given the set of entropies and the joint entropy for n sources, I can choose a large n so that I can make each source integral entropy. But the second part is, so in my assumption, it says that the concatenated alphabet of these forms a coset code. Okay, so this is my assumption. This has more significance. So in assumption 2, having integral entropy is not a major assumption. The only assumption is it also forms a coset code is a major assumption here. And why is that valid? For example, if you look at so if you take the joint PDF of the sources, of the n sources, and look at it as a noise of this particular channel. Okay, so if you look at the noise of, so the probability distribution on the noise is the joint PDF of the sources, and x, the input to this channel is and if this is the channel, the input is also belonging to the same alphabet, output also belongs to the same alphabet. So therefore this channel is symmetric in fact. Okay. So if this channel is symmetric, the capacity achieving this one on this is uniform PDF for X, right? So if you look at this channel, and for such a channel, we know that from linear coding literature there are capacity achieving linear codes, and let G be such capacity achieving linear code. And again, using the slide from the previous section where we had noise x1 and x2, when noise forms a coset code, we can represent x2 as a coset code. So the typical sequences of noise form a coset code with respect to the linear code G, which achieves capacity on the channel. Right? Okay. Therefore, the joint PDF forms a coset code. So this assumption is valid because you can always choose a channel and make it choose a linear code G such that it forms a coset code. Okay. So now looking at the group theoretic formulation of hypergraph. So let's say that this is a general hypergraph. Here the assumption 2 is not valid, only assumption 1, that it's regular, is valid. Okay. So we can define a group on the set of vertices. Okay. For example, I have chosen Z6, which is integers modulo 6, a group on this, and assign each vertex to a group. Okay. And this 03 forms a subgroup of this. So the idea here is, if you look at the subgroup and consider all possible edges over this subgroup, this indexes this graph in the sense that, so we define a group and subgroup on each of the vertex edge. Okay, and extension group is basically just concatenation of the two groups. So if you consider a group over this and a group over this, and if you consider the end of the concatenation of these two symbols, that also forms a group. It's called an extension group. And if you consider, so basically if you look at the joint PDF on this, that is if you look at this hypergraph, and if you look at this subgraph, this the cosets of this subgraph contain exactly one edge of the hypergraph. For example, if you take this, so on this graph there is only one edge, which is this. And if you consider a coset of this subgroup, basically shift this, let's say, to 1, 0, 1 and 1, 3. If you do 0, 1 and 1, 3, even that will have only one edge. So that means the hypergraph is forming a coset code for this subgroup. Okay.
Can you just repeat? I mean, how did you define the group? I mean, why did you order that vertices in that particular order? I mean,
This thing?
You're defining a group on each set of vertices, right? For
Yeah, it's not a random ordering. I chose
them.
Yeah. So basically, if you look at this, if I compress this and this, okay, and if I compress this and this, and if I compress this and this, I'll get a complete PDF n-parted graph, complete bipartite graph. And so I chose the first such set as my subgroup. Okay, so this set I chose my subgroup, and I index the others based on the as cosets.
For integer like this, modulo this, you know that what the subgroup, what indexes the subgroup will have.
Yeah.
So you found out the subgroups, like,
right,
and you.
Yeah, it's an assignment. It's not a random assignment. It's a assignment so that it achieves. The PDF hypergraph in fact forms a subgroup of this. So now from here we can observe that this is for a two-parted graph, but for a given hypergraph on n with order n, you can still if the graph has optimal or maximal compression achievable on it, then you can always specify a subgroup for which the graph becomes a coset code. Okay. So okay, the idea is basically you have a graph, and let's say that you can achieve maximal compression on it. And if you can achieve maximal compression on it, you can assign groups and subgroups such that the graph becomes a coset code of the subgroup. Okay?
Your thing is, did you prove that statement, or it is like a known fact?
Yeah, I did prove the statement.
So there is a proof?
Yeah. Okay, so this is one way. It says that if hypergraph is compressible, then I can specify a group structure. Now, the other way also, if you can specify a group structure so that the hypergraph becomes a coset code. For example, if the hypergraph forms a coset code based on this ordering, then you can always compress it. And the compression algorithm is basically in each coset, just send the coset index. For example, 0 and 3, just send only one of them. And if 2 and 5 can be compressed together, and 1 and 4 can be compressed together. So it holds both ways. Okay. So this is for a general group structure. But if you consider linear codes, I told you that you can index cosets in polynomial time, right? Because there is a generator matrix and a parity check matrix which indexes the coset. Therefore, this coset code indexing is polynomial time. Given a hypergraph where compression is achievable, then the encoding algorithm is polynomial time. It's very fast. So again, looking at coset codes. Now that was the general graph, but here the second assumption that it forms a coset code and it has integral entropy is satisfied. So if you represent each of them using a binary string, and this is the hypergraph, this forms a graph which indexes the coset. So you can look at this. This is basically a complete graph, complete n-parted graph, and this becomes a subgroup and it indexes the joint PDF. So now let's assume that okay. So here the special property okay, I'll go to the encoding algorithm that makes things more clearer. So let's say that a general algorithm where this is 8 vertices on the left hand. Now I am considering the two-source problem, and the generator matrix G is given by a column vector G1, 0, a common part GA and GB, 0 and G2. So now since this is okay, so if, for example, if this is my PDF hypergraph, so this satisfies the regularity assumption and everything. If this is my PDF hypergraph, and I am given that this indexes this matrix indexes the cosets for which the hypergraph forms a coset code. So that graph can be represented like this. So this is in fact the subgroup which indexes the cosets of the hypergraph. So basically I am considering this example just to show a general algorithm for compression, given that they form a coset code. Okay. So in this case, if G1, 0 and 0, G2 represent the G0, G1 subgroup is this, and actually this is 4, yeah. Okay. G1, 0 and 0, G2. This is a subgroup specified by this the complete n-parted graph over these two sets of vertices, and because of the common part, the subgroup gets separated like this. So the subgroup is not complete in this case, right? So in the previous case, the subgroup here is a complete n-parted hypergraph. So we had an immediate algorithm for compression, and the compression algorithm is basically take cosets of this, take cosets of this, take cosets of this, and combine them together. That's the compression algorithm. So in this case, we don't have immediate compression algorithm, but we know that if you compress this, and this, okay, you will not have a complete compression, but you will have, so I combine this with this, I'll get a new hypergraph, okay, and okay, so we took advantage of G1 0 and 0 G2. So if they are separable, we can compress them immediately. But if there is a common part, then we have to do something more to compress it. Okay. Now, in fact, we can observe that this. So we compress these two together, and these two together. So now this part, which is indexing the cosets of this, becomes a edge from here to here and an edge from here to here. Right? So in the new graph, edge from here to here and these two edges.
I think the details of this are completely lost on me. I don't know how anybody else feels, but I'm lost. So why don't we cut to the chase?
I think you should like wrap up this part and just like where is.
So okay, now the algorithm is described in the thesis. Basically, what I'm trying to do here is okay. You have a general generated matrix G, which indexes the joint alphabet. Okay. So if on two sources, you have two sources which form a coset code. That means there exists a generated matrix G which indexes the coset codes. Now I am trying to establish an algorithm wherein I can make this general G into a diagonal G so that distributed source coding is possible. Okay. So for that, what I do is I consider two cases. And basically I illustrated this using G with only 3 columns.
Yeah, I think for me that was the crux of the matter. You did some sort of diagonalization, right. So that's great. Details of it.
So yeah, once you diagonalize, you get parity check matrices for each of the diagonal elements, and you can encode for distributed source coding. You can encode them using just matrix multiplication, and that gives a distributed source coding.
That's enough, because there's no way you can explain these things in such a short time.
Okay. So for multiple sources, it's still the same thing. We consider all this as one part, and we consider the first source as one part. We do the compression, and then go about proceeding on the rest of it. Okay. And this need not give, even if there is a compression algorithm, this need not always yield a compression, because the order which we choose. Maybe changing the order and choosing all n total possible orderings will give a good algorithm.
So that's unknown.
Okay, now I use the algorithm I have specified on an example, which is pertinent maybe in synthetic or anything. It's a toy example. So basically what I have here is a binary source which transmits BPSK symbols, and each of them experiences a path loss coefficient to a sensor. These are the sensors. There are n sensors which are sensing this information. Okay. And each of them experiences a path loss coefficient.
Is that the F?
Yeah.
I get it.
Which is different
Then
from the other.
you should change it, it's confusing.
Okay.
I mean, it's not significant for simulation. Like when I go.
No, it's significant for your audience.
Okay.
But it's not a function, it's just a
It's just a
scaling.
yeah, it's a scale. Yeah.
This is another thing we can see.
Okay. So and they have independent Gaussian noise. So since the source is same, they are still correlated. The information here. Now I have the distributed source coding block. Okay. So and this is the block which I am trying to design here.
So each person gets they all get scaled copies of the same, scaled noisy copies of the same bit?
And they perform a hard decision decoder, hard decision. That is because these are dumb sensors.
Okay.
So they do a hard decision decoding, and then there is a buffering of n instances, which I will put into the distributed source coding block. So and then they are decoded at the center of the signal. So this is kind of the problem. We have a source which is transmitting BPSK information. There's sensors which are scattered around, and each of them is sensing the BPSK signal with the noise. And then the n instances are. So the thing is, now you can specify this as a joint probability distribution of each of the sources, right? So if you look at the joint distribution, so the number of sources is, now these sensors are trying to transmit to a central receiver. So the number of sources is the number of sensors, which is n, and number of instances you are trying to compress is capital N, and but you transmit capital K instances instead of capital E. That is where the compression is achieved. And the joint probability distribution function can be achieved because the path loss coefficient, the distances, everything is known. So the joint probability distribution for the while the sources is known. This is the position matrix is where the sensors are placed, is X. And what I am trying to show in the next slide is I have plotted, I have calculated 3 of these variables, which is Pn. So now, okay, I have n sources and a joint PDF P over them. All of them are binary, and I am taking n instances of them. So I have 2 to the n, 4 to the n possible sequences.
So n, big N has to do with the quantization, actually how you define correlation on what symbol.
I define correlation, yeah, the hypergraph is basically on the n symbol.
So your simulation has to do with the previous graph, right?
Yeah.
So the number of sources is small n is the number of sensors.
Yeah.
And the number of instances
Is the buffering.
Yes, the buffering. This one.
But buffering has to
It's like a block line.
Yeah, it's like a block of this one picture.
Yeah, it's the size of the alphabet.
Yes, the size of the alphabet.
That is like to maintain the regularity of something, right? I mean, if you
Yeah,
more
that's
than
right.
what happens?
Huh?
I mean, that is basically to maintain your regularity of something, right?
Yeah, basically I am trying to get a linear code. I know that linear codes achieve capacity on a channel with joint probability distribution as noise, right? So I'll use that linear code and encode the n instances for distributed source code using my algorithm. So the picture is basically like this. I know that if I am given a joint probability distribution function, there exists a linear code which achieves capacity for an equivalent noise channel. Now given that linear code, I can diagonalize it using distributed source coding algorithm. Okay, so what I do is I take that linear code, and how I design the linear code is I just random instantiate it because okay, I'll get to that later. So once I get the linear code which achieves capacity for the joint PDF, I do the distributed source coding algorithm. Sometimes it works, sometimes it doesn't work. Once it works, whenever it works, it gives the max whatever the linear code is. The performance of the linear code is reflected in the performance of the distributed code also.
So specifically, what do you think you're trying to accomplish here?
So basically a general algorithm for distributed source coding for multiple sources.
So this is it's sort of an odd example, right? Because it looks like you really want the receiver to know what the source said.
Yeah.
So it's really a communication problem.
It's more like this. Let's say that this is an enemy territory, something in an enemy territory, and you just deploy in an enemy territory, or basically some.
I don't understand what word you're saying.
Okay. Sorry.
Enemy. Oh, an enemy territory. All right, don't go back to that graph. Really
Okay, so if you look at this, this is kind of what you want to sense, but you can't be physically present here to sense it. So what you do is throw sensors here, wait for some time, let the sensor, and then come down and collect it.
So let's go to the next slide. All right. I don't know. There's a slide you missed, or maybe it's the previous slide. No.
The big slide.
That slide with the HDD block. There, that's fine. Right. So each one of those blocks is one of those sensors, right? And so physically, like, you want to minimize the rates of communication along there.
The total rate, the sum rate of.
And so you're sort of like it seems like you're punishing yourself pretty good using a hard decision at the center, aren't you?
I mean, I need not have a hard decision here. Let's say that I have a soft decision decoder. Okay, that will introduce a greater or higher alphabet probability distribution over this. Then instead of considering linear codes which achieve capacity on field 2, I'll consider linear codes which achieve capacity on a higher field.
So I mean, a lot of people working on sensors and relays work on this kind of a model,
Okay.
right? But they just keep changing what their objective is, right? Like you could, for instance, somebody else in the lab might be working on mechanisms where they signal something here and they minimize some energy function, right? Or some power function subject to some decodability over here, right?
I think most of the problems consider kind of a communication between the sensors. I really doubt that they consider a distributed source coding problem on multiple systems.
Well, I'm saying in a more general sense, like your real goal is to measure the bits.
Right, yeah.
And so there are a lot of problems that can be formulated.
Okay.
Right. All right, let's go ahead. We'll look at your results.
Okay.
He doesn't. I mean, right. That's one way of putting it.
And I guess like somebody would say, suppose you just had you don't, for instance, those wires, the lines back to the central thing, they all occur in orthogonal channels.
Okay.
Yes or no?
I mean, once you compress the information, everything is.
Those are.
Yeah, they are orthogonal.
Yeah.
You can, yeah.
Because like zillions of people have all looked at like the fact that you could do, I mean, if you could just do something dopey like amplify and forward and coherently combine a bunch of copies, then life is peachy.
That's what's his face. That's reasonable.
Yeah, a lot of people, that's sort of gas bars.
Yeah, that's
You have to quantize.
What do you mean? It's the algebra is, you don't have to quantize it.
You have to quantize. There's always an A to D in any receiver now that I think of. I haven't seen a receiver yet that doesn't have an A to D.
I give all these radios.
At least not in the last 20 years. You need
how do you store an analog value in order to coherently combine?
You record it on a big magnetic tape reel.
Oh, in a sensor?
So how many bits do you need for the analog representation?
The line is not here, right?
You just have the extent to which you quantize a good thing, you're just putting a little quantization noise in. It doesn't change the fact that they all.
You can measure how much.
Okay, but let's keep going and we'll. Okay.
So the parameters for my simulation are basically the number of sensors, the number of instances, and number of instances I choose to sense, overall instances.
Yeah, what is T, a probability distribution?
Yeah, it's the vector of all possible probabilities over 2 to the n size algebra. It's basically the joint probability of n sources. Joint probability distribution vector of n.
It's the two ends.
Number of sources.
So is it like a probability measure on the received signal?
It's actually the joint probability of the binary sources, which is each of them is a binary source, right? So they have a joint probability distribution over there. So P is basically the joint probability distribution.
So it's basically just a probability measure for everything random in the experiment.
Yeah.
Yeah. Okay.
So now I am comparing 3 of them. First thing is, let's say that all these sources. Okay, if all the sources combine together and then compress the information, then what they have So given there are n instances in each of the sources, I am taking a total of k instances. So the total size of the alphabet they can transmit is n into capital N, right? N into capital N bits, but they are sending only k bits. So I choose the 2 to the k maximum likely bits in the 2 to the n bits. Okay, that gives a measure of what is the maximum performance you can achieve for a given for the given number of bits you want to transmit. So PM is the set of sum of the all maximum likelihood 2 to the k sequences of all possible sequences. Okay.
At any one transmitter? I would have thought all the sequences are actually probable. All 2 to the cap n sequences that.
No, they are not equiprobable. It's more like as you take more instances, you'll have a set which are equiprobable and you'll have a set which is probabilistic.
Oh,
right?
N is large, then you get the A.
So I am taking 2 to the k maximum
okay,
probability.
so the source is BPSK, but it's not 0, 1. It's not half a half.
It's half a half for each source, but the joint PDF is not.
Wait,
equal.
the source is the thing on the left. No, like let's go to that block diagram.
Yeah. So this is the source now.
Okay, but so this thing called binary source.
This thing is this thing gives the correlation to each of the source.
So are the sources after
So the marginals are 50-50.
Yeah.
The distribution itself is not
the
trivial.
original binary source.
Right. That gives the correlation to each of the sensors.
Is a half minus 1 or 1.
It is a half
Right. Then looking at your sequences of length n, like, right?
Caption noise.
Okay, all right, I understand.
Okay.
All right. So you're sort of like finding the k most typical thing.
Yeah.
The
2 to the k most typical thing.
Yeah. Okay. All right.
Okay. That gives PM. That gives a measure of how much we can achieve using linear codes or any code for that matter. Now PJ is basically the joint, the maximum probability with which you can send a sequence, okay, using a linear code and joint compression. Now for every possible G I generate to get the PJ, I try to obtain the distributed source coding bound. If I don't get it, if I get it, PD will be equal to PJ. Okay.
I always was under the impression that likelihood is a single word.
Yeah.
Yeah,
You also have the framework in your pieces.
Doesn't have Y.
So let's not do grammar right there.
I'm thinking my bad.
Okay, so this is the final simulation where you have 2 sources here and 3 sources here. These are less significant, which is where the sources are placed, where the sensors are placed. This is the joint probability. You can see that the marginals are in fact 0.5, 0.5, but it's very skewed distribution. It's highly correlated data. Even here the correlation is very high for 3 sources. Now for n is equal to 2, I take 2 instances and I transmit 1 instance. Okay. Then the maximum probability, the maximum likelihood probability is 0.9843. If I choose a linear code, I can still achieve 0.9843. Okay. But distributed code doesn't achieve that good here. But as we go close towards the entropy, for example, here